Hello, I welcome you all to this another interesting screencast. The problem reads if the coefficient of static friction at the contact points A and B is mu s equal to 0.3, determine the maximum force P that can be applied without causing the 100 kg spool to move. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we're going to be dealing with what is called dry friction. So what is dry friction? This is the force that resists the movement of two contacting surfaces that slide relative to each other. So this is a force that resists the movement of two contacting surfaces that slide relative to each other. So the maximum friction itself is equal to F equal to mu, which is the coefficient of friction, times the normal force. So in all the problems we're going to be dealing with in this particular chapter, they are going to be of three types of dry friction problems. The first one is where we are experiencing no impending motion. No impending motion, by this we mean the number of unknowns are less than or equal to the number of equations of equilibrium. So if this is the case, it means we can solve this particular problem by the available equations of equilibrium, and after we've done so, then we need to check for slip where F is less than mu n. If this condition is met, then we know that there is not going to be any slip at the contacting surfaces. The second type is where we are going to experience impending motion. Okay, we are going to experience impending motion at some contacting points or surfaces. This is where we're going to have impending motion at some contacting points or surfaces. In this particular case, the number of unknowns are going to be more than the available equations of equilibrium. Okay. Alright, and if this is the case, therefore we are going to be forced to add additional equations, and we are going to invoke or use the friction equation F equal to mu n. The third case is where we have impending motion at all contacting points or surfaces, or contacting points, okay, or surfaces. Okay, in this particular case, this condition again applies, which we just used in the second case. Let me just copy it down. I bring it down here like so. So this condition also applies. The number of unknowns are greater than the number of equations of equilibrium. Therefore, we are forced to use additional equation which from the friction itself, or the friction equation. So the second and third here, we need to assume, we need to have the correct direction, of F in our free body diagram. Here we are free to assume the direction of F. Only in the first case we are free to assume. Even when you assume the wrong direction, you are going to get a negative to just mean it was in the other side, or it was supposed to be the other side. In the second and third, the moment the number of unknowns are more than the available equations of equilibrium, here we don't have the luxury to assume. We need the correct direction of F in our free body diagram. Here we can assume the direction of F in our free body diagram. So basically, these are the steps. These are the mechanical steps. You follow them, you arrive at the answer. Okay. You can check out these particular steps in the same book by Hibbeler, Statics Engineering Mechanics textbook by R.C. Hibbeler. All right. Let's start doing the work here. First things first, let's draw the free body diagram. This has some weight, so the weight is going to be acting at the center of gravity. Let's say that is our center of gravity. We're going to have a normal force there, and then this, if you look at this tends to move in this direction like so. This spool, right, tends to move like this. Okay, therefore our friction is going to be in the opposite direction of that. Okay, every time we are working out this particular problem, you need to ensure that you assume the right direction. Okay, because you only know that after you've started. You only be sure unless the unknowns are less than or equal to the available equations of equilibrium. All right. So since this tends to rotate in the anticlockwise, then we need our friction is going to be in this direction like so. Okay. So our friction is going to be in that direction like so. Like so. Okay. Here we're going to have a normal force, and then we'll have uh, our friction like so. All right. So basically, this is about it. Let's just label them. So we say this is our W, and this one here is our normal force. Let's call it NA. This one here is our friction. Let's call it FA. This one here is our normal force. Let's call it NB. And this one here is our friction. Let's call it FB. All right. So what's the question again? The question is to determine the maximum value of P that can be applied without causing this 100 kg spool to move. So let's find what this W is. W is just going to be equal to mg, which is just 100 times 9.81, and this is going to be equal to of course this is just 981, right, newtons. Let's count the number of unknowns. Number of unknowns. How many are there? We have 1, 2, 3, 4, 5, right? We have 5 unknowns. Number of equations of equilibrium. How many are there? 3. So how many equations are we short of? Because you can only find the unknowns if the number of unknowns are equal to the number of equations, right? Available equations. So we need to use additional equations, friction equations. So we'll say we need one equation, FA equal to mu S times NA, and this is just going to be equal to 0.3 NA. We also need another one, which is FB equal to mu S by NB. This is also just going to be equal to 0.3 NB. So this condition, we are experiencing what is called impending motion. Okay, we are going to experience what is called impending motion at all points of contact, impending motion at all the contacting points. Okay, that is at A and B. So at all contacting points, which is A and B. Okay. All right. So having said that, then let's start applying our equations of equilibrium. Okay. Let's start with summation of forces in the x. So say summation of forces in the x direction equal to 0, going this direction being our reference. So in the x we have NA, okay, minus FB equal to 0. Okay. And we know that, therefore, we know that FB is also equal to 0.3 NB. And therefore, NA is equal to FB, which is equal to 0.3 NB. Okay. So let's go to another one. Summation of forces in the y equal to 0. Going up in our reference, we have minus NB. No, sorry, this is positive. NB positive minus W plus P plus FA equal to 0. Okay. All right. Okay. What else? Let's take moments. Let's say about point A. So say summation of moments about point A equal to 0, and clockwise being our reference. So we are going to have a minus moment, that is W by what's a lever arm 0.9. Okay, and then we have plus NB by 0.9. Okay, and then we have plus, this is of course this FB is a minus, minus FB by what's this distance here? Of course we know that this distance here, let me just show it. This distance here is equal to, this is equal to 0.9 minus 0.6, which is equal to 0.3, right? Of course. Okay, there we go. So FB is FB, this is this distance here, which is just equal to that's 0.6. Okay, up to there, up to that point there. So this is 0.9. Okay, and then we have plus P up to there. Of course, from here to there, that's 1.2, and then 1.2 plus 0.3, that is 1.5. Okay, so this is 1.5 like so, equal to 0. Alright, so found what NA is, which is equal to FB, and we know what FB is. So let's work out the two equations. We work out the two equations. We know that FA is equal to 0.3 NA. So we are going to the place where we have FA. We replace so that we have additional equations. We generate equations that we can solve simultaneously. So let's do so. Let's just write down these equations on top. Alright, so let's start with the first one there. So we are saying NB, this summation of forces in the Y, minus W, okay, plus P, then plus FA, and we know FA is just 0.3 NA equal to 0. But we already found what NA is. We said NA is equal to 0.03 NB, right? From this equation, summation of forces in the X. So we can replace this in there. So this becomes that's 0.3 by 0.3, which is 0.009 rather. So this becomes NB minus W plus P plus, of course, we replace there, this becomes a 0.09 NB equal to 0. So if we are to add this just becomes a 1.09 NB minus W plus P equal to 0. So we have one equation. Let's work out the other one there. Summation of forces, moments about point A. So this is a 0.9 W plus 0.9 NB, okay, and then we have minus 0.9 NB. So these two, they go, right? Okay, so this part goes. Where was this? Summation of moments about point A. We have NB, okay, we are taking moments about point this. Alright, okay, this is NB, sorry, this is 0.9, sorry, this is 0.9 NB minus 0.9 FB plus 1.5 P equal to 0. So we know that FB is equal to 0.3 NB, so we can replace that there and then sum it up and then write it. So we'll have 0.9 minus 0.9 by 0.3. Okay, so this becomes a 0.63 NB minus 0.9 W, okay, and then plus 1.5 P equal to 0. Right, 0.9 minus 0.9 by 0.3. Alright, so we have two equations. Let's just write them side by side so that we can work on them. So we have this one. Let me just put it somewhere there. And then we have this one. Okay. There we go. Something like this. Okay. Something like so. Great. So let's solve these particular two equations. So what we are going to do is, let's see what we can get rid of. Of course, we get rid of the unknown so that we remain with what we want to find. We want to find P, so we are better off removing NB. Okay, right? So let's do so. So we need to remove NB. So I'll multiply this side by 1.09, this side by 0.63, and then just do subtraction. This is substitution method, and then so that we work out this problem. So we have a minus 0.9 by 1.09 by 981 plus a 663 by 981 equals minus 1.5 by 1.09 P plus 0.63 by P. Alright, therefore P max is just going to be equal to, so minus 0.9 by 1.09 by 981 plus 0.63 by 981, okay, then divided by minus 1.5 by 1.09 plus 0.63. Okay. Alright, so our P max is just equal to a 342.62 newtons, right? Alright, let me repeat this. Minus 0.9 by 1.09 by 981 plus 0.63 by 981 divided by minus 0.5 by 1.09 plus 0.63, so 342.62. Great. So this is the maximum value of P that can be applied without causing the spool to move. Alright, but mind you, like we said, there is impending motion, so it means the moment we increase this P max by even a 0.01, then the slip takes place. Okay, so I hope this particular video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.